All right, I'm pretty glad to be here and excited about this topic actually. But I'm just going to get right into it. I have a lot of stuff today. In fact, if you have a hard time seeing small words, you might want to move up a little bit. But if you're good, then that's fine as well. I'm trying to make these words the smallest that I get. So if you can read that, you're good probably. If you can't, it's okay. You can come up. But we had at Kuali, we have a lot of self-steering product teams, and each of these teams have their own AWS accounts. And in doing that, we found that there was a lot of different ways people were managing their AWS accounts, but what really was happening is they just go in the AWS console and click around and click until it did what they wanted it to do. And oftentimes they'd make changes and things would break and nobody would discover the broken thing till the next day, and then they'd forget that the changes were made or that it was even related to the broken thing at hand. And so we wanted all our changes to be in version control, and trying to figure out the best tool to put all changes to our security groups, to any of the things that we rely on in our AWS infrastructure to be changed through the same process that code gets changed through. Have peer reviews, have tests on the change, and then put it into production and make the change go live as soon as we merge our code into the master branch. And this includes everything from VPCs to all of the things that we rely on at Kuali in AWS. It also creates, we wanted to create some consistency across teams, the different product teams, to be able to use the similar tool sets and solve this problem kind of cohesively, but also allow our teams to remain self-steering. So in order to do that, we came up with a solution to use SaltStack to manage all the infrastructure. We've seen a lot of its abilities, and then we wanted to run SaltStack in a Dockerized container, and doing that allows each team to use this tool portable. They can run it anywhere where they prefer. And today we actually run it in, we can run it locally on our laptops. We can run it in, we run it in code build, in AWS code build, and we actually run it in our ECS clusters as well. But it can be run in many different places. But the idea is it'll provide a portability for the people to implement their changes wherever they need to run their code from. And also, in putting in a container, our engineers don't have to maintain a Saltmaster. They don't have to configure and set up a Saltmaster for every AWS account that exists. And of course, Git, we already talked about why we need the version control. And so what I'm going to do now is I'm going to kind of talk about what the tool does and what our end users are required to do to use this SaltStack tool that we've built in order to make their infrastructure come to be. So the first thing they need is an external pillar. And I'm glad if any of you just went to the previous session, the breakout session with Pillar, you already know what the external pillar is. And this one uses Git as an external pillar. And you also need some environment variables. And then you run the Salt Minion containerized and that's all you need. So you need Docker. You need to create some environment variables and pass them into your containerized image. So the external pillar, it lives externally in a Git repository. This is the only thing the end users need to maintain to use this tool. And so it's really, really simple for our engineers across to manage all the different AWS accounts that we have at Kuali. So here's an example of a VPC pillar that would exist in a Git repo. It's very simple. You want to create a VPC, you just say, hey, I want a VPC, tell it which region you want, give it a name, and actually the name is the next item there, and then give it a CIDR block and say, yeah, I want an internet gateway. Let's make it true. So this is exactly, and I have the examples in this. This is a public Git repo here. All the examples I show in here are in that repo. And that'll go ahead and once you execute the tool with the appropriate environment variables, everything will come to be. So this is a subnets example. So if we want to add subnets, you can go in right in there and say, hey, we want some subnets. We want it to be in this region. We want it to be in that VPC. That's the next item on there. Right here, this is the VPC name. And then we want these these subnets to exist, and we want one of them to have a NAT gateway. We just put true in there. And then it will go out and create all of those subnets with the NAT gateway. For routes, we need our routing tables. And so we want to have different route tables for our private subnets and a different route table for our public subnets. So here we do the same thing. We say, hey, we want some route tables in US West 1. We want a public route table, and it needs to be in this VPC right here. And here's the routes. We just have a default gateway to the internet, and it needs to use our internet gateway that was created. And we're doing these by names. This is the other nice thing about using Salt. Some of the other tools, you got to get the IDs, you got to remember what they are. It's very hard to read. And with Salt, we made it in such a way that we can do everything based off the names. So it's a little easier, human readable and understandable for our engineers to know what is actually there. And then when they go look at it, they say, oh, this is the same name. They don't have to sit and translate IDs and all of the other things that gets complicated when building out infrastructure. And then, of course, in our private subnet route, or our private route table, we have a different internet or default gate route, and that default route uses the NAT gateway that exists in this subnet. And that's all we had to do there. And then when you run the image in a container, a Docker container, you have to pass it some environment variables to make this actually work. So I've kind of shown you some of the code in the pillar data in the Git repository, but we need to have some environment variables so that our container, our image, can know where to retrieve the code and how to execute it. So we pass it an AWS key and key ID, whoops. And this will give it the permissions to make changes in our AWS account. So for each account, you're gonna have a different AWS key and a different key ID. And then we need to pass it a GitHub repo, tell it where to go get the configuration externally, and know that tells it what to apply. So it needs the repo, the passer, the username, the password, and the branch. And then we also allow for some Slack notifications during changes. So you can pass it a Slack channel and a Slack token, and it'll kind of post in Slack what's happening live. And then we also have an environment variable test. So if you pass test equals true, it's going to do a dry run and tell you what would change if you run this without test. And with all these things, it gives us a really good foundation for automating our infrastructure. So I do have a demo, and I'm just going to demo some of the basic stuff right here. And I did the demo previously, so let's hope this works here. And I'm just going to talk through it as it goes along. So we are playing. Right here, it's really, really small. I thought I went through and made this as big as I could. But in here, this is our Git repo, and this is the one that's public. You can look at it today. And this was a little bit older version, but we have two files so far, a top file and a VPC file. So in the top file, we just say, hey, here's the pillar that we want available to any minion that runs this, and it's the VPC SLS. And then in the VPC SLS, we say, okay, here's our VPC. And this is actually the exact same code that I just showed you guys in the slides. So we've got that code, except it's all in one file. And so we've defined the VPC, the subnets, and the routes. And it's all here in our Git repo in one file. So that goes through the same things. I'm going to go a little bit fast forward because we already went through all of those things. So now what I'm going to do is I'm going to show you what this is our Docker container. And I'm using Docker Compose. And what I've got here is I've created two little configurations. One's a test run, and one's a production run. So we want it to actually make changes. The other is just to test our changes. And the only difference between the two is the environment files. And remember, those environment files are going to pass all my environment variables that I showed you as needed to run this. And I'll show you a masked version of those environment files because I don't want to give out all my keys and passwords. But yeah. Let's see, we'll skip ahead here. So there's a version of the masked environment file, and then there's the difference of the test file. The only difference between the two is one says test equals true, and the other doesn't. So that's the only difference between the two environments I created here. And so what we're going to do first is we're going to run the test to see what should happen. And so let's see. There we go. So I'm going to run a Docker Compose run saltconf19-test. So it's just gonna run this image that we've created or that exists, and it will go out, retrieve all the data from GitHub right here, and it'll go through and take all the pillar data and make it exist the way that it needs to. But in this case, I'm running tests, so it's just doing a dry run. And there we go. So it actually says there's 9 resources. All of them are set to be created. And so now that we know that the test works, and that's actually what we expected because none of it exists already. So now let's go ahead and run it real. I think I might have skipped where I showed in the AWS console that it doesn't exist yet. But now I'm running it for real, and we should be able to see now that, did I skip that part? Oh, did you see it? So yeah, right here, there's no VPCs, there's no subnets, there's no route tables. So let's go ahead and run it for real. And now it says it actually created all of those resources. So if we go back into AWS now, we can see, there we go. We've got a VPC, our demo VPC. We've got all the 4 subnets that we've created. And we've got the route tables, the 2 route tables that were defined. This is really small. I think the next demos are a little bit bigger that I've got. But all those resources now exist. And they can be maintained in a state. So if anyone tries to edit them and this tool gets run again, it'll revert them back into the place it needs to be as defined in code. Any questions at this point in time? So I'm using in this demo, I'm using the Salt's execute or state modules that exist natively in the open source version of SaltStack. They have some Salt Cloud states. And what I haven't shown you yet is the formula I used to render this pillar data, but I will get into that next. So I'm going to show you how I built the tool that we used. But this is what our engineers use right now, and this is their experience with it. No, so this is actually mutable, right? So it's going to go in and see if it's there, and if it's in the state that it thinks it should be in, and if it's not, it'll change it to be to the correct state. So it's stateful, yeah. Yes, we do. So we do VPC peering and accept peering, but we had to write some custom execution modules to get some of this stuff to work the way we wanted to. But so far what I've shown you is all built in with, it comes with SaltStack. But I will tell you that we do write a bunch of execution modules ourselves in order to get some of the other things that we want. So let's see. There's that demo. How are we doing on time? Okay. So that kind of showed the basics there of our infrastructure. We also do S3. Here's an S3 pillar example. So, and we have a documentation that shows how to format all of our pillar for our engineers at our company so that they don't have to know Salt, they don't have to understand Salt. All they have to know is if I structure my pillar data like this is going to exist, right? And so this example right here actually shows an S3 bucket that is a public website. So this one will become a public website, and you can or a static website. So you can control all that. You have the website, you've got the error, HTML, the index, you've got everything that's allowed, including who has access to the S3 bucket. And this one's not, obviously it says some user role, so this is just an example. I'm not going to do that demo. So let's talk about what's inside the tool. What's in the image that we've created, the Docker image. So we get the Salt minion is all we put in there. So we don't require a Salt master. We just use a Salt minion and everything that SaltStack brings with it. We do have some custom Salt formulas, some custom Salt execution modules, and some custom state modules. And maybe even, I can't remember, I redid some of the Slack returner to make the Slack returner work a little better, but that's a little custom too. And these are the formulas we support today inside this image, the Docker image. So we can create users, we can do code build jobs, AWS code build jobs, we do ECS tasks and services, scaling groups for ECS, we do EFS, ELBs, ALBs, so that's a custom, let's see, the code build's custom, ECS is custom. I can't remember if EFS, I think EFS is custom. Our ELB comes with SaltStack, but the ALBs is a custom execution module. IAM roles and policies are native or open in the open source version. SSH key pairs we do. VPC peers, I think that one exists, but there was a lot of bugs in that. We had to change that one. And then routes exist, S3 and security groups, subnets, target groups. Target groups is custom as well, and VPCs exists already. So those are the salt formulas we provide to our engineers, that they can do any of these things within this tool. And we're constantly adding new things. That's what's another reason why we chose Salt, is because we can customize this to meet the needs that our engineers have. So here's the formula. This is an example formula. If you can't see it, this is even a kind of a simplified version of our formula, because I have some other things in there that usually check if absent is in your pillar, I'll actually remove that resource from AWS. But if it's not, then it will go make sure it exists in the way that it's there. So I think I pulled out the absent just for simplicity. But what we're doing here is, if you notice, we're actually getting, the Salt has an execution module called environment.get, and it'll get the environment variables. So when you run this in a containerized, your image in a container, it'll just pull out from those environment variables and stick it right here in this formula and apply it in there so that you can make these changes happen. So we're really just running the Bodo VPC subnet present. And that's what we're doing. And so it goes through and it runs a for loop in our pillar data, pulls out all of the subnets that exist in the pillar data, and just runs a subnet present on it. And then we also say, if gateway is true, we want to create a NAT gateway for that subnet as well. And we're just doing the Bodo VPC NAT gateway present. And these are built-in executions or state modules that exist in SaltStack. And that's as simple as our formula is. That's all we have to maintain. And we can now create subnets just with pillar in our external pillar. So we do that same thing for each of those, for each of these right here. We have a formula for every one of these items, both a remove and a present, both the absent and present. And that way we can remove objects in our infrastructure or create or update. So how do we create the tool? This can be debated on if this was the best way to do it. Actually, a lot of this can be debated, but we just use a CentOS Docker image and put salt minion on there. We configure it, the minion config, to accept external pillars. So I don't know if you know, but Salt master configurations can have external pillars, but so can Salt minions. And so that's what we're doing here. We just put the external pillar config in the minion config inside this image. And then we have to install all the Python libraries required for AWS. So there are some Bodo libraries that need to exist for AWS in order for those execution modules to work. And then, of course, we do have some custom code that we put in this image as well. So I'm actually going to go through the minion config. This is the one special piece that makes it so that it'll go out and get our external pillar. So we actually use our minion config. We create a template to create our minion config. And this is just a snippet out of that template that says, hey, if your GitHub repo exists as an environment variable, then go ahead and create this external pillar and point to the exact GitHub repo that you need to point to pull down your pillar data. So this is kind of the secret sauce, right? And then it also puts in the GitHub user and password. So this is how the minion knows where to get the data, and then from the salt formulas can apply it with the other AWS environment variables that we pass to the container. All right, and then this is the Docker file. This is how we create our image. And I've kind of stripped a few things out of this as well, but basically we just want to, we need to install, we need to add the SaltStack repo so we can install a salt minion. And then we need to update and add the EPEL release to get some of the libraries that are required. We need to install pip and get some more Bodo stuff and PyGit. PyGit's required for our external pillar. And I can't remember why PyC parser is there, but I think that's required for PyGit as well. And then we install Salt itself on the image, the Docker image. And then we remove all kind of traces of it, and we make our serve salt directory. And then part 2 of the Docker file, we now need to copy all of our custom execution modules in there. So I'm not going to show you what those are today. Some of those, hopefully I'd like to contribute a little more to SaltStack and maybe get some of this stuff up there. But we copy in all of our custom execution modules or custom state modules, and then we actually run a apply salt minion. And what that does is it allows us to get the minion config in the way we want it before the people actually run the image in a container. Let's see. We also copy the initial script that we use to run, to allow people to, the entry point essentially. We create an entry point, and that's pretty much it. That's how we create our Docker image that we run. Now the nice thing is I do pin the versions here, so I know that it's always going to work with our pillar data, right? And so when we move forward with newer versions, we'll be able to test in an appropriate way, so we don't break everything. We still have these versions that exist forever, and so if we add some new feature and then we kind of deprecate another feature, then at least the people that are using, the engineers that are using something deprecated can always use that image that was older to keep and maintain their existing infrastructure pillar data. But that hasn't been an issue at this point. This is our just script that we run that basically says, hey, if you're running a test, then make sure we do AWS test equals true. Otherwise, we don't do it. And we also do a ret code pass-through. And the reason we do that is because we run this image inside of AWS code build. And in order for code build to know if the test passed or not, we have to pass through, we have to do a ret code pass through. So the return code, if there's any failures in our test, it'll tell AWS code build that this was a failed test. And how we do that is we actually have our AWS code build tied into GitHub webhooks, so that when we do PRs, it automatically runs a code build job that then runs that PR branch on automatically and does a dry run with it, and then outputs the test of that. So if that test fails, it'll notify right in our PR that, hey, this is a bad infrastructure change right off the bat before it gets merged into production. And then we also do the same thing with when we merge to master, we have another code build job that runs automatically and applies all those changes without test. It does an actual run. Other stuff. So I've kind of talked a little bit about this. We do some Slack integrations, custom execution modules, custom state modules, and then an advanced feature that we kind of built. So we try to stay true to our state modules and having them do only what they need to do. But we did create one kind of wrapper state module called the Kuali container service. And what it does is it takes all of our other execution modules and makes it easy for our developers to do a very simple app deploy. And it looks, let's see. Oh boy, I didn't put an example in there. I forgot to put that in here. But what it does, it takes like a few lines of pillar code and it allows you to, and I do have an example of that and I'll show that. Let's see, other stuff. Automated testing, I talked about this already. And then the benefits. So let's talk about this and then we will have time for questions. And then I also have another demo that I want to show. Version control. So again, we get to see when changes are made, who made them, who approved them, and exactly what time they were done. We also get to test our changes so that people aren't just going in anymore. It's not the Wild West. We don't just click through, oh, I think this isn't communicating to this, so I'm going to change my security group. And oh, wait, that didn't work, but I'm going to leave it that way anyway because it doesn't seem to break anything. And then things just change and nobody knows who's changing it and when and how. And so we're trying to get rid of all the Wild West changes into our infrastructure and move to something that everyone can see. And we also needed it to be portable. We couldn't run one single Saltmaster because every team is so self-steering and they do their own thing. And so this tool had to be able to work in any AWS account. So this works in n number of AWS accounts. And it can be run from anywhere. So if some of the other engineering teams, product teams don't do what the others do, if they don't like their used code build, they can run it in maybe Circle CI or in their Kubernetes cluster or wherever they want to run it. And it's pretty easy to use. You don't have to understand the details of Salt to get this to work. You just have to be able to read the documents on how the pillar structure needs to look in order to make it happen. And of course, you can always test it as well. That's very important for engineers because they want to see if this is going to do what they think it does before they actually commit this code to master their pillar data. I want to give a shout out. He deserves his own slide. Joel Woodbury, he helped write a lot of the execution modules in there that are custom. And so I just want to put his name in there. He's been a big contributor to this at Kuali. Been a big help. Any questions at this point? Yeah. Yeah. Yeah, it has. And it's what our company uses for all of our code. And so, you could actually use any sort of Git repo, but we've used GitHub. Yeah. Oh, okay, yeah. So the container itself is always the same, but what it produces is the infrastructure which can be changed. Does that make sense? Yeah, so the infrastructure that it's producing, the tool is immutable, but the infrastructure it's creating can be changed in AWS. Does that make sense? Okay. Yeah, say that one more time. How did you give them a sandbox that they can make changes and play with things without having to make 20 pull requests when things don't go wrong, and how they don't actually need your assistance? So with Docker containers, there's quite a few tricks in there, and so the question was, how do we test this without changing live, essentially? How do we allow the engineers to test this without doing things that they might break? And so because it's a container, you can run it locally on your host, and you can actually, the test mode is very important, and then giving them a region or somewhere where they can actually run the tests on live if they want to is also helpful. But you can actually pass in to a container, instead of telling it to go to a GitHub repo, you can have it point to local disk and pull the pillar locally. And so we do that a lot of times in our test environments where just say, hey, here's your pillar locally, and then just don't commit anything yet until you feel good about it, and you can run that container locally in a test environment or somewhere else and make sure that testing works the way that you need to without having to commit to your pillar repository for your infrastructure. And so you can kind of test things out there. Does that help answer the question? Yes. Yeah. They don't have to understand it, but if they want to, they can definitely dive into the image, and they can look at it. They can look around, see what's happening, and they can even submit changes to it because we have a different repository for managing the tool itself as well, and changes can be submitted to that. Any other questions? Okay, I'm going to show one more demo, and this is a demonstration of how we do like a Hello World web app. So if we want to do it, so right here it's showing we've got an ECS cluster. There's no clusters that exist right now. So one thing we want to do is we want to create an ECS cluster. And then after that, we're going to want to create some load balancers and target groups, and then create a service that runs in our ECS cluster and a task a task that our service runs, tell it how many tasks to run, how much memory it's needed, and then make all that happen. And that sounds like a lot of work, and it actually is, but we do it with like less than 20 lines of pillar. And so I've made this commit, and here's our pillar data right here. This is what's required to create an ECS cluster. All we need to do is say, hey, we need an ECS cluster, it needs to be in this region, here's its name, go. And then for our Hello World web application, it looks like this. And this is our custom secret sauce here. So we say, hey, let's make a cluster or a new web application. We're going to call it Hello World. We're actually going to give it a DNS name, and we're going to tell it to run one container count. And here's our task definition, or our container definition. It tells it where to pull the Docker image, which is from Docker Hub. It's just going to pull the Hello World Docker image, and then it's going to give it 256 megabytes of memory, and it tells it which port the container runs on, and so that we can pass that through to our load balancer, which we're also going to tell our load balancer to be internet facing and run just the HTTP protocol. We have the ability to do a lot more than this, but this is just a quick run through. And so now I'm going to run this again in the way I ran the previous one. I'm not going to test it this time because we've already done this. But if any of you have ever interacted with AWS, it actually takes a long time for your load balancers to come up. And so I ran that, and we're going to look here and actually see the stuff go as it happens. So starting up a load balancer in AWS takes about 5 minutes. So this demo takes that long. We can fast forward if needs to. But we can start to see Salt doing this as it needs to. On subsequent runs of this, it's not going to take 5 minutes to run because the load balancer already exists. So if you want to change it from HTTP to HTTPS, it'll be much quicker. And we can make changes to our existing deployed applications. So in here, now we have our target group. So our target group exists, and our load balancer is currently provisioning. And so it's going to provision that load balancer. It's going to make all this happen. And once that's provisioned, it will then go in and create the service in our ECS cluster and the tasks that are needed to run. So I'm going to skip a little forward. It's still running because this does, okay, there we go. So it went from provisioning to active. So now that it's active, we can see that we're going to come over to our ECS cluster. And there's the listeners. It's got the port 80 listener. And it's pointed to the target group, and the target group is actually pointed to that container or that service in our ECS cluster. So if we refresh that now, we can see we have a service there, and our states are completely run. They're fully run now. So we created our cluster, our ECS cluster, and then we also created our web application, or we deployed our web application from another Docker image with a fully functioning load balancer. DNS is created, the container or the service is created, and it's got its memory allocation and the tasks that it needs to run. And there you go, the DNS worked as well. It points to that load balancer, which is the load balancer that was created. So that's as easy as it is in Salt to use this same container to deploy our applications. So we can put this application pillar data right in our same repository as our application itself, and then just pass along the things that it needs to launch it into our AWS ECS clusters. Now, the only one thing I didn't do here is our ECS clusters don't have any running instances, so the app never actually went live, but as soon as I add a running instance in that cluster, that app would just start right up. And that's the last of that demo, or the end of that demo. And I think we're about 10 minutes early, so unless there's any other questions, I think we're done.